Welcome back to Simplifying Synthesis, the channel where we look at complex organic chemistry and explain how it works. In this video, we are going to look at a detailed overview of conformational analysis. I'd like to start this video with a big thank you to my patrons. I really appreciate the support. And to all my viewers, whose likes and subscribes help this channel grow. This video is quite comprehensive, so if you find the first section too simple, feel free to skip ahead. So what is conformational analysis? Structures that can be interconverted by simple rotation about single bonds, without any bonds breaking or forming, are said to be conformations of the same molecule. Conformational analysis studies the energy of different conformations to predict the most stable conformation and how this affects the reactivity and bioactivity of the molecule. So first, let's look at alkanes. The most common way to visualize alkane conformations is by using Newman projections. These show an end-on view of the molecule, looking down the axis of a carbon-carbon bond. The carbon atom at the front is depicted as the intersection between the substituents, and the carbon at the back is drawn as a circle. From this view, we can see the substituents extending out and the angle which is between them. This angle is called the dihedral angle, often abbreviated to theta. So let's look at ethane, which is the simplest system. In ethane, there are two notable conformations, staggered and eclipsed. In the staggered conformation, the dihedral angle is 60 degrees. This maximizes the distance between hydrogen atoms on the adjacent carbons and is the lowest energy conformation. In the eclipsed conformation, however, it is an energy maxima and is approximately 12 kilojoules per mole higher in energy. This has a dihedral angle of 0 degrees, and by convention, the Newman projection is drawn slightly offset so all the substituents are visible. There are two explanations for why the eclipsed conformation is higher in energy than the staggered conformation. The first is repulsion between the CH sigma bond orbitals. This is highest in the eclipsed conformation as they are closest together and experience van der Waals repulsion. The second is hyperconjugation between CH sigma bond orbitals and CH sigma star antibonding orbitals. This hyperconjugation stabilizes the molecule when it is in a staggered conformation. When the molecule adopts an eclipsed conformation, it loses this stabilizing effect, which increases its energy. So let's move on to butane. Unlike ethane, not all of the substituents are equivalent. This gives rise to different eclipsed and staggered conformations. For example, we can have a staggered conformation where the terminal carbon groups have a dihedral angle of 60 degrees, or we can have a staggered conformation where the dihedral angle is 180 degrees. To account for these different conformations, we must introduce a new naming system. This system is known as Klein-Prelog nomenclature. If the substituents are on the same side, that is, within 90 degrees, it is given the prefix syn. If it is on the opposite side, it is called anti. When it is 60 degrees, plus or minus 30, it is called synclinal, which is more commonly known as gauche. Substituents that are 120 degrees, plus or minus 30, are called anticlinal, whereas if the substituent is 180 degrees away, it is called antiperiplanar. Following this around, we get another anticlinal and synclinal conformation. These are differentiated by including the direction of rotation, which is given a plus or a minus. These conformations can be abbreviated to a two-letter symbol and the directional designation. With this nomenclature, we can now accurately describe all the conformations of butane. The highest energy state is syn-periplanar, which is the eclipsed conformation. This moves into a staggered synclinal conformation, which then raises in energy to an anticlinal conformation, which then falls to the lowest energy state, which is antiperiplanar. In this conformation, there is a dihedral angle of 180 degrees between the carbon groups. This pattern then repeats with a change in the directional designation from minus to plus. So now, let's look at pentane, which is the last simple alkane we will look at. In pentane, we must consider the conformation around the C2-C3 bond and also the conformation around the C3-C4 bond. In its lowest energy state, both are in the antiperiplanar conformation. However, we can rotate one of these bonds, in this example the C3-C4 bond, and arrive at two different conformations, an antiperiplanar conformation on the C2-C3 axis, and a plus synclinal conformation along the C3-C4. As the conformation around both of these bonds can be varied, pentane has a large number of possible conformations. However, two in particular are very important. These are called syn-pentane conformations, and it arises when there is a synclinal conformation around both of these bond axes. In these conformations, pentane has an energy maxima, and this is due to 1,3-dimethyl eclipsing interactions. These syn-pentane interactions are very important and are responsible for the conformation of many natural products, including polyketides and the backbone structure of proteins. So let's look at discodermalide as an example. Hairpin bends are introduced into the structure to avoid syn-pentane interactions. These occur at the C10-C12 region, where we can see there's a hydrogen in one of the axial positions, and also at the C16-C18 and C18-C20 region, where again a hydrogen atom takes the axial position, as it is the smallest substituent and generates the least repulsion. So now, let's move on and look at systems with double bonds. The first interaction we will look at is allylic 1,2 strain. We can see this in molecules such as propene, which is shown here. In this molecule, the conformation where the double bond is eclipsed by a hydrogen is actually the more favoured conformation, which may appear counterintuitive. However, when we look at the orbital structure of the molecule, it makes a lot more sense. There is repulsion between the carbon-hydrogen sigma bond when it lies in the plane of the carbon-carbon pi bond, which destabilizes the staggered conformation. When it is in the eclipse conformation, there is only one interaction between the pi bond and a filled sigma bond. This interaction is not limited to carbon-carbon double bonds, but also carbons bonded to heteroatoms, such as in aldehydes. We can see this kind of interaction in butane, where the lowest energy conformation is where the double bond is eclipsed with a hydrogen atom, and the methyl group is pointed away from the double bond to minimize repulsion. A more significant type of strain encountered in double-bonded systems is allylic 1,3 strain. This is steric repulsion between substituents on C1 and C3. It is critical for the conformations of alkenes, imines, enolates, and other double-bonded systems, particularly when C1 is chiral. This strain forces molecules to adopt the lowest energy conformation, where the smallest group on C1 will be orientated toward the substituent on C3. We can see this allylic strain in the backbone of discodermalide. It occurs between C7 and C10, C12 and C15, and also between C20 and C23. In all of these locations on the molecule, 1,3 allylic strain is minimized by adopting a conformation where a hydrogen atom is placed in the most sterically hindering position. Allylic strain is not limited to just alkenes. It is also present in systems containing heteroatoms, such as amides. Amides have a flat planar structure due to the delocalization of the lone pair of the nitrogen with the carbonyl group. It is this resonance contributor which is responsible for the allylic strain observed in amides. As we will see later in this video, substituents on 6-membered rings prefer to occupy the equatorial position, to minimize steric hindrance. However, in this amide, the methyl groups adopt an axial conformation, and this is due to the allylic strain between the carbonyl oxygen and the methyl group when it is in the equatorial position. It is possible to take advantage of this allylic strain in stereoselective synthesis, as is exemplified by Evans' chiral auxiliary. Reaction of the oxazolidanone with the base generates an enolate. Due to the allylic strain, only one isomer of this enolate will be generated. While at first glance it may appear that either of the protons may be deprotonated, a closer examination of the orbital requirements for deprotonation reveal that there is only one proton which is favourably deprotonated due to the stereoelectronic requirement for the carbon-hydrogen bond to be in the plane of the carbon-oxygen pi antibonding orbital. So now let's move forward and let's look at conformational analysis in cyclic systems. As we saw in the guide to rules for ring closure, there are several different types of strain which occur in rings. The first of these is Bayer strain. This is the deviation of the carbon-carbon bond angle away from the ideal value of 109.5 degrees. It is worth noting that these values assume a flat planar structure, and saturated rings will often pucker and adopt a conformation which reduces this strain. The next strain we will look at is torsional strain. As we saw earlier, there is a stabilizing effect that occurs when an antiperiplanar relationship is adopted due to hyperconjugation between carbon-carbon bonding orbitals and carbon-carbon antibonding orbitals. The ring structure forces the molecule to twist away from this ideal orientation and adopt a synclinal conformation, and this destabilizing effect is known as torsional strain, sometimes referred to as Pitzer strain. Related to this is van der Waals repulsion, which occurs on eclipsing substituents. While this contributes to torsional strain, it is less significant than the hyperconjugation effects. One of the most important effects in the conformation of cyclic systems are 1,3 diaxial interactions. This is repulsion between axial substituents that bear a 1,3 relationship on a cyclic molecule. Rings will often flip to put the largest substituents in the equatorial position in order to minimize the strain. This strain is similar to the syn-pentane interactions which we saw earlier in acyclic molecules. So let's take a closer look at the conformations of cyclohexane. The lowest energy conformation is the chair. Straightening one side of this structure generates a half-chair conformation, which is the highest energy state for cyclohexane. Continuing this motion, it can then adopt a twist boat conformation, which is slightly lower in energy than the boat conformation, which is sometimes seen. These conformational changes then repeat on the other side of the ring to go through another twist boat and half-chair conformation to arrive back at a chair. As was noted earlier, cyclohexane can flip to put substituents in either an axial or equatorial position. This happens by one end of the chair moving up, while the other end moves down. This inverts the conformation of all of the carbon centers present in the molecule. The magnitude of the preference of a substituent to adopt an equatorial position over an axial position is given by the A value. This is derived from the equilibrium constant between these two conformations, and by convention is given in units of kilocal per mole. As we can see in this example, as the R group gets bigger, the A value increases. This correlates with the increasing steric hindrance of the larger groups, which suffers larger 1,3 diaxial repulsion. It is important to note that increasing the group size does not always correlate with an increasing steric demand. Changing the atom which is bonded to the ring can cause deviations from this trend. Atoms with larger covalent radii decrease the steric demand, as the larger radius means the group is further away from the axial hydrogen atoms. We can see this in the example. By changing the atom bonded to the ring from carbon to silicon to germanium and tin, the A value decreases as the bond length increases. The nature of the ring can also impact the A value. Rings with heteroatoms, such as nitrogen or oxygen, can increase the A value due to their shorter bonds, which brings the axial groups closer together and generates an increased 1,3 diaxial repulsion. Likewise, if we introduce a larger atom, such as sulfur, the A value decreases as the bond length increases and the axial groups are further away. An important effect in rings bearing a heteroatom is the anomeric effect. This is the preference for a heteroatom substituent to occupy the axial position when adjacent to an endocyclic heteroatom. This can overcome the preference for equatorial substitution and is especially important in carbohydrate chemistry. There are two main explanations for this effect. The first is hyperconjugation between the non-bonding electrons of the endocyclic oxygen and the sigma star antibonding orbital of the exocyclic carbon-oxygen bond. This can only occur when the group is in the axial position, as this gives an anti-periplanar orientation between the orbitals and allows overlap. A second explanation for this effect is dipole-dipole repulsion. When the heteroatom substituent is in the axial position, the dipoles orientate in opposite directions, whereas when it is in the equatorial position, they orientate in the same direction, which causes repulsion and destabilization. So let's look at discodermalide again and the influence of diaxial strain on its conformation. The lactone ring adopts a boat conformation, and the C5 side chain, the C3 hydroxyl group, and both C2 and C4 methyl groups occupy equatorial positions. This conformation minimizes the diaxial strain by putting the smaller hydrogens in the axial position. Keeping with cyclic structures, we can also look at fused systems, when two rings are joined by two atoms. An important molecule in this group is decalin, which is formed from two six-membered rings joined at two atoms. There are two conformations: cis-decalin, which has both hydrogens on the same side of the ring junction and can interconvert between two conformations, and also trans-decalin, which has hydrogen atoms on opposite sides of the ring junction and is locked into one conformation, as it is impossible for one of the rings to flip and form a diaxial ring junction due to the strain within the small ring system. In fused systems, conformational transmission can be observed. This is when the conformation of one ring influences the conformation of the ring fused to it. In cyclohexane, the dihedral angle is 56 degrees for every carbon-carbon bond in the molecule. However, when you introduce a double bond into the structure, this flattens part of the molecule and changes the dihedral angle to 15 degrees adjacent to the double bond, 44 degrees for the next bond away, and 61 degrees for the bond directly opposite in the ring. We can describe the strain placed on the ring by the change in the dihedral angle from the optimal chair conformation, and also use arrows to show if it is contracting or expanding, as shown here in the example for cyclohexane. This conformational transmission can be seen in the formation of enolates. In the first example shown here, there are two possible sites for deprotonation, and the products are formed in a 1:9 ratio. When the site closest to the ring junction is deprotonated, there are opposing effects introduced by both alkenes, where the enolate is causing the contraction of the fused bond, and the alkene is introducing an expansion of that bond. Whereas deprotonating on the other side of the carbonyl causes an expansion of the dihedral angle on the fused carbon-carbon bond, which reinforces the effect caused by the alkene. If we look at the second example, where the double bond is placed in a different position, we can see the opposite effect, where we get a ratio of 92:8, this time favouring deprotonation at the site closest to the fused bond. Once again, this is due to reinforcing effects, where the contraction of the dihedral angle is reinforced by both alkenes in one isomer and is opposed in the other. This conformational transmission can occur over quite long distances. In this example shown here, a fluorescent molecule was designed with a metal coordinating site on one side of the molecule, three fused six-membered rings in the middle forming a linker, and also two pyrene groups on the other side. Without a metal present, the bipyridal substituents are in the axial conformation, and the pyrene groups are in the equatorial position. This allows for the formation of a fluorescent Xmer. This is where the two pyrene groups interact via pi stacking interactions, and then, when fluorescently excited, form a short-lived complex with a fluorescent emission at 480 nanometers. The introduction of zinc triflate triggers the formation of a coordination complex, which brings the two bipyridal groups closer together, forcing them into an equatorial conformation, which causes the inversion of the three fused rings, which places the pyrene groups in the axial conformation. In this conformation, they are too far away to form an Xmer, and their fluorescent emission is shifted to 380 nanometers. This is only possible due to the cis-Decalin type ring linkage, which is able to convert between conformations, as the trans-isomer is rigid and inflexible. So now that we've covered the basic principles of conformation analysis, let's look at how these effects influence synthesis. In cyclic molecules, whether a group is axial or equatorial can greatly influence its reactivity. As a general rule, SN2 substitutions of axial groups tend to be faster due to the more accessible LUMO orbital, which allows the nucleophile to approach from an unhindered path. Equatorial groups tend to react faster as nucleophiles, and this is because the HOMO orbital is more accessible, as it isn't blocked by axial groups, such as the hydrogens shown here. A model commonly used to explain the reactivity of carbonyl groups is the Felkin-Ahn model. This model suggests that the largest group on the alpha carbon will adopt a conformation perpendicular to the carbonyl carbon-oxygen bond. In this conformation, nucleophiles will attack from the Bürgi-Dunitz angle of 107 degrees, approaching from the side of the smallest substituent. It is possible, however, to overcome this preference. This can be done using chelation control in a model sometimes referred to as the Cram chelate. This is possible when there is a substituent adjacent to the carbonyl group which is capable of coordinating to a metal. In the example shown here, we can see that the Felkin product is formed when the carbonyl group is reduced with a lithium-based reagent. As lithium is a small monovalent ion, it is not good at chelating between two groups. This reaction therefore forms the Felkin product, as steric effects determine the outcome of the reaction. Using a zinc-based reagent allows for chelation to occur between the carbonyl oxygen and the sulfur group. This holds these two groups in an eclipsing conformation, and the hydride will now approach from the opposite direction. This chelation control is possible as zinc is a large dicationic metal and readily forms chelation products. Chelation control can also be used in aldol reactions by holding the two reactants together and having the stereochemistry of the product determined by the most stable conformation of the transition state. This was used in the total synthesis of spirochancellide A. In this reaction, an enolate was reacted with an aldehyde in the presence of a boron salt, which generated a single isomer. By examining the transition state, we can see that the chelation of the boron by the two oxygen groups allows for the formation of a chair-like transition state, where the furan group is in the equatorial position, which minimizes 1,3 diaxial interactions. It is this chelation that drives the formation of a single isomer. The stereochemical outcome of cyclohexanone reductions can also be driven by torsion effects. Small reducing agents, such as lithium in ammonia, preferentially attack from the axial position and form a product with a hydroxyl group in the equatorial conformation. This might seem unexpected, but a closer examination of the conformations shows why this occurs. If the hydride approaches from the equatorial position, the carbonyl oxygen must pass through an eclipsing interaction with a hydrogen atom on the alpha carbon in order to adopt the equatorial position. This eclipsing interaction presents a torsional barrier which drives the preference for attack from the axial position. This preference can be overcome by using a large reducing agent. Larger reagents are more sterically demanding, and in this case, the axial approach is blocked by the axial hydrogens and forces the reagent to take the equatorial approach due to steric repulsion. This steric effect overcomes any torsional barriers. We saw the effects of the conformation of 6-membered rings in the total synthesis of fluganine I. In the reaction shown here, the striker reagent adds a hydride to the conjugate position, which generates a silylated enolate type intermediate, which is protonated to reform a carbonyl. This reaction was highly selective, and we can employ the Curtin-Hammett principle to explain it. Simply put, the Curtin-Hammett principle states that the diastereoselectivity of a reaction is influenced by the energy of the different transition states, and not just the energy of the starting materials or the products. So to explain this reaction, let's look at the conformations possible to form the product. The enolate type intermediate will adopt a half-chair conformation. If this is protonated from the bottom phase, it must pass through a twist boat-like transition state, which then produces a product with the large butynylide group in the axial position, which suffers from 1,3-diaxial repulsion with hydroxyl and hydrogen groups. This can flip to put it into the equatorial position. However, this also increases the energy of activation. As the twist boat transition state is a high energy intermediate, it is disfavored. If the half-chair intermediate is protonated at the top phase, however, it forms a chair-like transition state and produces a product with the butynylide group in the equatorial position. This is a much lower energy pathway and explains why this product was formed in the reaction. So let's finish up with some carbohydrate chemistry and look at conformational effects in glycosylations. These are reactions which attach carbohydrates to other molecules. This can be other carbohydrates or any other molecule which has a suitable nucleophile. The general glycosylation process starts with a protected glycosyl donor which has a leaving group at the anomeric position. This is the position next to the endocyclic oxygen and is always numbered as the 1 position. This glycosyl donor will typically exist in the chair conformation, known as 4C1. The C denotes a chair conformation. The superscript 4 and the subscript 1 show that the conformation has the 4 carbon higher than the 1 carbon. To perform the reaction, an activator is then added, which promotes the leaving group to leave the molecule, and this generates an oxocarbenium intermediate. This will exist in the half-chair conformation, which is here named 4H3. The glycosyl acceptor will then add to the anomeric position to form the glycoside, which reverts back to a 4C1 chair conformation. It is possible to fine-tune the reactivity of these glycosyl donors by using protecting groups which affect the conformation of the molecule. Glycosyl donors are deactivated by using electron-withdrawing protecting groups, which slows the expulsion of the leaving group. Super disarmed donors, however, also exploit conformational effects, which utilize cyclic protecting groups which lock the donor in the chair conformation and make it harder to form the necessary 4HC half-chair intermediate due to the high torsion strain put on the ring systems. Likewise, it is also possible to superarm donors by using conformational effects. These use sterically hindered protecting groups, such as TBS, which are forced to adopt the axial conformation due to the steric repulsion which is experienced when they are in an equatorial position. Depending on the nature of the groups used, this will force the molecule into either a 1C4 chair conformation or a 3S1 skew boat conformation. There have been numerous explanations proposed as to why this conformational superarming occurs. One explanation is that axial groups are less electron withdrawing, and this is because there is no antiperiplanar relationship with the pyrran oxygen that would allow hyperconjugation from the filled carbon-oxygen endocyclic bond to the empty sigma star carbon-oxygen antibonding orbital on the adjacent carbon bonded to the OTBS group. As it is less electron withdrawing, the ring is more activated and the leaving group can leave easier. Another possible explanation is charge stabilization through charge dipole interactions. With the oxygen substituents in axial conformations, they orientate towards the positively charged oxocarbenium moiety. This provides some stabilization and reduces the energy necessary to form the intermediate. A further explanation is that the axial-rich donors occupy a conformation which is closer to that of the half-chair intermediate. When the leaving group leaves, there is donation from the lone pair of the oxygen into the carbon-oxygen bond to form the oxocarbenium intermediate. The oxygen must therefore move upwards to form the flat planar surface required for the half-chair conformation. When it is in the 1C4 conformation, this is a smaller change than when it is in the 4C1, which produces more torsional strain to adopt the half-chair conformation. So I think at this stage of the video, I've covered all the main points of conformational analysis and shown how they can be used to analyse the conformation of natural structures and how they can be exploited in synthesis. So to summarise, the conformation is determined by balancing repulsive and stabilising forces. These include steric and stereoelectronic effects, and the substituents and functional groups present on a molecule can greatly influence its conformation, even that of remote groups. It is not just the conformation of a molecule, but also that of the transition state, which can determine the outcome of a reaction. So that's everything for this week on simplifying synthesis. If you found this guide useful, please like and subscribe, and if you want to see anything, let me know in the comments down below. Next week, I'll be looking at the total synthesis of cotyledon A,